Okay, welcome to class, everybody. We're going to start with a quick demo. So I asked my TA to go to the bookstore and find some cheesy LED toys, like this laser blaster, right? Or this, I don't know how to turn this one on, right there. Or this flashing Skeletor, right? We're going to do something. We're going to do an experiment. I'm curious what you guys think will happen. We're going to take this, and I'm going to dip it in liquid nitrogen, okay? So I'm going to try and just dip the LED part in liquid nitrogen. And so the question I have for you is, what will happen, right? So turn to your neighbor. Should anything happen? What's going to happen? We dip the LED in the liquid nitrogen. Who's got a thought on what might occur? What do you think? The color might change? Do we have a reason why that might happen? Because what? Gut. She's going with her gut. And the color might change. The color is going to change, right? So the question is, okay, if the color does change, let's do the demo, okay? Any of my TAs here? They're not. My TAs have found better things to do. Andrew, can I bug you to come help me real quick? So I'm gonna have him film it because it's a little bit hard to see. So we'll just turn on the camera here. I'm gonna have you hold the camera and not see my face, but instead you're gonna hold this kind of like that. Okay?
Yeah.
So go for it. He's gonna hang on to that for us. So the first thing I want you guys to see is the color initially, right? The color is like a bright red. You guys see that? Like a bright, bright red. Okay, we're going to dip it and see what happens. Okay. So I'm going to let it... So can you kind of see what's happening in here? So I'm just trying to dip like the barrel of the gun from the bookstore. Why does the bookstore sell these? I don't understand. Let it get very cold. I don't want to cool down the battery because it might not work. But just the LED. Okay, now when I do it, what color is it now? It's like an orange. It's definitely changed color. Let's try with the skeleton head, because we have the skeleton head. Okay, again, skeleton head initially, very red. Okay, let's try it when we dip it, see what it does. That's an awesome visual. Steam shooting out of the top of the skull. Okay, let it get good and cold. It's probably all right. Okay, what color is it? Dripping out of it. Very orange. You guys see that? Way orange. Okay, so red LEDs turn orange. This is like dripping liquid nitrogen. Okay, thank you so much. We're going to show you a quick YouTube video that does a different color. Let's see what happens here. Here they've got a blue LED, which he's going to dip in liquid nitrogen. Okay, so he's pouring out the liquid nitrogen. He's going to dip this in it. If red turned orange, this one turns purple. Definitely turning purple. Okay? So what's going on, right? Let's pull up our electromagnetic spectrum. So color, spectrum, wavelength. So first off, they shifted color. That means that the wavelength shifted. Did they both shift the same direction? So if you had red and you went to orange, then you shifted to the right. This is called a blue shift, right? You shifted towards the UV spectrum, right? And then the one that was blue shifted purple, so it also shifted right. So in both cases, with two different LEDs, well, three, I guess, if you count the skull, right? In three cases, putting in liquid nitrogen caused a blue shift in the color. Why? Somebody got some sort of explanation? Andrew, what do you got for us?
At cooler temperatures, there's a higher probability of them occupying higher energy levels.
Oh, that's a good guess. So, what we've been talking about this chapter, you're thinking of the right things. It had to do with like these Fermi distributions, and we said that the higher the energy, the higher the temperature, the more thermal energy, more these things can hop. So it makes sense that the intensity of light will change, because the intensity is a function of how many of these things are available, and an LED works by recombining these. And if you're at a lower temperature, let me go down to our recombination, right? If you're at a lower temperature, there's just fewer of these things there, so there's less recombination can occur. So what you're arguing should affect the intensity of the light, but not the wavelength, right? So why does the wavelength change? What do you think, Avery? This band gap, this is what gives you the color. So these are they're blue shifting, which means the band gap is doing what when we cool it down? It's getting bigger, right? The band gap, why is the band gap changing? Why is it changing? Well, what's changing when you cool it down? Yeah, Harley.
Is the actual metal shrinking itself?
Yeah, absolutely. There's a thermal contraction, and that is accomplished by vacancies a tiny bit, but mostly due to atoms just squeezing, just like people, right? When it gets cold out, we sort of huddle together. Atoms are doing the same thing. They come closer together, and if we go all the way back to the beginning of this chapter, go all the way back to band diagrams, right here. If you make this distance a little bit smaller, you open up that band gap a little bit. And we've seen it with color, right? So I liked this demo that Matt was great enough to remind me of, because it brings together so many concepts we've talked about. It's band gaps are related to light and color, of course, but those are related to the interatomic spacing, and other things can affect band gap. So let me ask you this. If you were starting with some semiconductor material, and you wanted to change its color, but you don't have temperature as a control, what would you do? Or in other words, right, the same blue LED you saw in the video, if you wanted to make a purple LED, but you don't want to dip it in liquid nitrogen, you want to work at room temperature, what do you do to that structure? What would you do? Turn to your neighbor. What would you do to that semiconductor? Okay, what do you do? Temperature's not an option. You can't just change the temperature to get the color change. What do you do? You're all so close to being engineers, right? You're going to get hired tomorrow maybe for some company, and they say, first order of business, we need some purple LEDs. What do we do? Right? You could dope it. What will doping do? It'll adjust the band gap how? Yeah. Let's say you started out with gallium arsenide. If you swap out gallium for another group 3 element, meaning you're not changing the number of electrons, you're just changing the size of the group 3 element. So whatever's above gallium. What's above gallium? Aluminum? I think it's aluminum, right? Let's pull this up. Okay, you've got gallium. Yeah, so you put some aluminum on there. Because aluminum's further up, it's probably a smaller element. The trend is usually they get larger the further down you go. So it's smaller. So that might lead to a contraction of the lattice. If the lattice contracts, you're going to change your band gap probably, right? And that's what they do. That's Elias and Avery, they're exactly right. As you start out with different things, some of these have what we know as solid solubility between them. So let's say you start out with gallium antimonide. Well, you could substitute gallium for indium, and that's going to give you a different size of your lattice, right? So the x-axis is the size of your lattice, and the y-axis is the band gap for all these things. So if you make them along this series, this is what your band gap does. It changes. Maybe you start out with aluminum antimonide and you go down to there. It's a really steep change. And then the thing to note is that on this y-axis, within a certain range, try to make this. if your band gap is within this range of energy, you get these colors. So if you wanted to change it, right, let's say you start out with cadmium telluride, all the way up to zinc sulfide, you could swap out these atoms, start out with cadmium telluride, go to cadmium sulfide, and you're going to change your colors from, here it's about green, down to red. So in the early days of LEDs, when we were first figuring out these things for solid-state lighting, it's great to have a laser pointer. That's great. But what we want for lighting is white light. People don't want to live in like a red LED lit room. So like having just CAD-TEL, that's not very useful, right? We want white light. How do we get white light today? It's all the colors of light, right? You want all of them. So you have options here. You could make a bank of arrays with lots of alternating band gaps, put all sorts of things along this spectrum all over the place. That's one option. A better option is to do a red, a green, and a blue, right? Your primary colors, and have them all have the same intensity. Now, the tricky part to that is getting them all to have the same intensity. Let's see. Let's see what comes up. Come on, Google. Don't let me down. Here you go. To get white light, you have to tune between these three colors. You really want to be right there. And then depending on the application, you might want it to be like a warm light, right? People in their homes actually want warm lighting. They don't want blue shifted. And in the early days, if you had it, LEDs were a little bit blue shifted, and it felt kind of like a hospital. It was kind of sterile. It was just slightly not quite white. I'd say in the early days of this, we knew how to do red and we knew how to do green LEDs. Red was first. Like the red laser was the first laser we made. A laser is just an LED that you just collect those things and then put them all in sync with one another, right? That's a laser. It's just a big LED essentially. Green we figured out to do, but for the longest time we didn't know how to do blue. And it wasn't that long ago that the blue LED got figured out. This was 2 years ago's Nobel Prize winner in physics, was Shuji Nakamura, for the blue LED, right? Which now we have like all over the place. You don't think anything of it. But for a while, this took a while to figure out how to do that. And actually a guy in our department, Jerry Stringfellow, this was like his life's work, was figuring out how to dope semiconductors to get different band gaps, because that has huge implications on solid-state lighting, where now today you can get LED lights for your homes which are incredibly efficient, way more than incandescent lighting, and that was possible by material science. Okay? So I thought that was a cool tie-in to what we're learning about. So let's dive into today's stuff. What we're going to finish this chapter, I hope we finish it. We'll get awful close if not. We have to talk about how electrical conductivity works for ceramics and for polymers. Okay? We also need to introduce a class of materials that don't conduct electricity, but they're a special class. They're not just insulators. We call these dielectrics, and they do something really interesting. Along that, we'll talk about how do dielectrics work. To do that, we're going to need to introduce different types of polarization mechanisms, something called dielectric breakdown. And then there's a really cool application of dielectric materials called piezoelectrics and ferroelectrics, and we're going to get into that at the very end of class. So let's start with ceramics and polymers. For the longest time, these things weren't thought of as being typically very good electrical conductors. If you were taking like a dinner plate and you put like an ohm meter up to it, you're probably going to get overload. No current's going to pass through that for the majority of ceramics. There's a reason that we coat electrical wires with the little polymer sheaths, because polymers, generally speaking, don't conduct electricity. That just means that they've got a big band gap, right? In our band diagram approach, we would say that means that the Fermi level is in the middle of that band gap, the valence band is totally full, conduction band is totally empty, and the reason it's empty is because it's such a big gap. But they figured out ways to get conductivity. For one thing, they realized that ceramics can conduct ions, but might not be able to conduct electricity. Or in other words, right, let's go back, way back to a few classes ago, you had the fuel cell, right? Remember in the fuel cell, the way that fuel cell vehicles work is you have pure oxygen on one side, and you have air on the other side, right? Or fuel, like hydrogen, right? You can run it lots of ways. But you have to have a difference in your oxygen potential on either side, right? So there's high oxygen and low oxygen. Your material, it allows oxygen ions to transport through the material. So literally oxygen turns into O2+, and it can hop through vacancies maybe, all the way through the lattice. But electrons can't travel through it, right? So instead, the electrons, right, let's draw it. The electrons do this. So our oxygen over here, that's O2, and this is O2, but let's say this is a high O2 and this is a low O2. So oxygen wants to travel that way, and we've said that only oxygen 2- ions can do so. Well, oxygen over here isn't 2-, right? So it's got to react. Let's actually do, so let's say you've got something like H2 gas over here. H2, when the oxygen gets there, it's going to turn into H2O, which is why these are such awesome devices, because the only output is water vapor, right? But this H2 starts out 0 charge as H2, and it ends up +1 charge. So that hydrogen is giving up electrons, right? Electrons are surrendered at this interface, right? From the 2- ions, right? These 2- ions are shuttling electrons there. Basically, they're shuttling charge there, right? The electrons travel outside of the circuit, though. So they come over here, they combine with your O2, so you get 1/2 of an O2 molecule, picking up 2 electrons to form O2-. That's 1 half-cell reaction, right? But the key thing here is that the electrons travel outside of the circuit, and that's how they can charge your cell, like power your cell phone, power your car, whatever else, right? So this was only made possible because we have a material that will not conduct electrons, but will conduct ions. And ceramics are interesting in that some of the best materials that do that are ceramics. Not only ceramics. Polymers can do it too, but ceramics do a good job of it. Okay? So you can conduct ions, or you can conduct electrons, or in some cases you can conduct both, right? So some materials are designed to conduct both. So your overall conductivity, electrical conductivity, it can have contributions from ions or electrons, right? If we go back up to this drawing, as oxygen 2- travels through that material, it's carrying electrons with it, right? It has an electrical charge, right? It's a great big ion, whereas electrons are tiny. So the speed of this, you typically think of it as being like much, much faster than electrons traveling through your material. But you might design a material where there's lots and lots of these ions, so the concentration of them is really high. So even though they don't hop very fast, because there's lots of them moving, you can get a significant charge. And so we need to introduce something called the transference number. And the transference number, I don't have it here. The transference number is just the ratio of one over the other. So let's say it's like ionic divided by total. So it's just going to be a fraction. Maybe it's like 0.5. If it's 0.5, that means that half of your electrical conductivity comes from ions being able to move through your material. And half of it comes from electrons. And basically there's materials that are all across this transference number spectrum, from being totally electrical conductors like copper. Copper is maybe not a good conductor of ions, but it's a great conductor of electrons, all the way over to like YSZ, which does not conduct electrons, but does conduct oxygen vacancies. And everything in between. Like cerium oxide is a great mixed conductor. Electrons and ions can both travel through it. Okay? With ionic conductivity, we use our expression a little bit differently. So here's the mobility of ions. The mobility, remember, think of that, that's like our friction. The higher the mobility, the less friction that the atom must be feeling because it's very mobile. So what goes into mobility of ions as opposed to electrons? The key thing is you have to have that diffusion term in there, right? So D sub I, that's going to be the diffusion coefficient for that ionic species in whatever host lattice there is, right? But otherwise it looks the same. You've got N, right, your carrier concentration. You've got E, the charge of this thing, D, and then over to thermal energy, okay? All right, what about polymers? Again, most polymers are not good conductors. Yeah, Sam, question?
For the diffusion coefficient, if it's not given, can we find that in the equation?
Yeah, absolutely. Yeah. So if I gave you an activation energy and a pre-exponential for diffusion of, say, oxygen in YSZ lattice, then you could figure out the diffusion coefficient at any temperature using our old friend the Arrhenius equation. Right? Now, polymers, we don't think of them as being conductors, and there's chemistry reasons on why that is, but the band gap reason is the useful one for us. Again, think of it like this. You've got your conduction band, you've got your valence band. This thing is chock full of electrons, and to get up to that conduction band, it's just a large band gap. That works equally well for describing polymers. In I think it was like the early 70s, this was another Nobel Prize, a guy at UCSB named Heger, Alan Heger maybe? He came up with this really clever idea on how to get a partially filled band. Because if you could just move your Fermi level down here so that your electrons are in the middle of a partially filled band, it should conduct electricity. And the way that he did that is with alternating double bonds in what we call a conjugated polymer, right? So it's like a single bond, double bond, single, double. And what that leads to is a half-filled band, right? So they did this, I think, in like polyacetylene. Yeah, polyacetylene was one of the first ones, at least in the early days of this. And then once they figured out how that works, well, you can put an alternating bond in lots and lots of polymers. And now I'm sure there's other ways of getting conducting polymers, but this was what won the Nobel Prize. And all of a sudden, you can have plastics which conduct electricity, which is critical if we're ever going to reach our Star Wars, Star Trek dreams of having, a newspaper TV you can fold up, open it up, and like foldable electronics, right? These had to happen because polymers are flexible, whereas ceramics or semiconductors are extremely brittle and rigid. So this allows us to introduce ductile electronics, which is pretty rad. Okay? And these are not like sci-fi. Like, these exist today. That is an LED that is completely polymer-based, right? So to have an LED, we know how to make LEDs. We learned about it. You have to have a P-type material. You have to have an N-type material, right? And so they had to figure out not only a way to make polymers conduct electricity, they had to figure out a way to dope them to either have mostly holes or mostly electrons so that you can create something like a green LED. And then if you want to change the color of that, you had to figure out how to get the band gap to change, right? So there's a lot of work here, and we're just like skimming the surface of there's a lot of research that goes into optical properties and understanding them for different electronic materials. I just want to say that they exist and that you should be aware that they exist. Okay, let's shift gears to dielectrics. Dielectrics are insulators, but they're special types of insulators, and they're ones that generate a large polarization in the presence of an electric field. What do I mean by that? What I mean is, it goes back to your days when you took physics. You probably saw an example like this of a parallel plate capacitor. I hope you learned about a parallel plate capacitor. Weird. My pen is freaking out. So if you've got a parallel plate capacitor, geez, it's not working. My electronic pen has run out of ink, which is bizarre. If I put a bunch of, I think that the tip broke. I think I dropped it, and it's broken. Anyways, if you put a bunch of positive charge on one side, I hook a battery up to a metal plate, and I put the positive voltage on that top side, I will accumulate positive charge there, right? If I do and then if the negative, and that will only happen if the negative is connected to this bottom plate, right? And you'll accumulate negative charge here. So that accumulating surface charge on a plate, that is at the heart of these capacitors. That is really weird. Time to replace that. Okay? So the question is, do all materials accumulate the same amount of charge on the surface for a given voltage? Right? So the voltage is maybe, say, a 9-volt battery, and this distance isn't changing. Let's say it's the same for all of our materials. It's 1 millimeter. If the voltage and the distance are the same, that means that the electric field across this is the same. It's not changing. It's the same electric field. But what we find in nature is that for that same electric field, the amount of charge that can be accumulated on these varies like crazy. Okay? So why? Why is that? The reason why is because some materials are dielectrics which enhance this polarization or this surface charge, right? The amount of charge we can fit on that surface. Okay? So let's step back a bit. There's something called the C, right? That's our capacitor, or the capacitance of a parallel plate capacitor, C. If you want to put more charge on there, you could do two things. First thing you could do is increase the area, right? Make the parallel plate surface area as large as possible, and you will put more charge there, right? You'll have a larger capacitance. The second thing you can do is make them as thinner and thinner together, and the reason why that changes it is because it leads to a larger electric field. So either of those things, either increasing A or decreasing D right there, will lead to a larger capacitance. But these are both, in this case, where it's in a vacuum between there, right? Vacuum means that epsilon naught, that's the permittivity of free space, which you would have learned about at some point in physics. That is so weird. It's a constant, right? It's not changing. What is happening? That is just bizarre. If you want to do it with a material inside, you accumulate more charge. So why on earth, when you put a material inside of this, do you accumulate more charge? This was like the big question. Like they didn't understand why that was happening. So what's happening is that the material inside can be polarized. So think back to Gen Chem. What does it mean when something is polarized? Electrically polarized. What does that mean? You end up with a positive side and a negative side. So let's just think of water molecules for a minute. You've got H2O, which is a bent molecule. You've got the O, and you've got the two H's, right? Water is a polar molecule. Polar because it has a charge built into it. You don't have to apply a voltage to this thing to get a charge. It has a charge because it's got these two lone pairs on this side. This is it wants the bond more than the hydrogen does, and so you end up with a positive one like that. It's got a built-in dipole, right? Anybody seen notation like that? Is this not the first time you're seeing it, I hope? Right? Because the oxygen wants a little bit more, it's slightly negative and it's slightly positive, right? So imagine that you build a parallel plate capacitor and you put a bunch of pure water between it. It has to be totally pure because if it's not pure, it will conduct electricity, and we don't want to conduct electricity, right? A capacitor relies on us building up charge between these surfaces, and if there's not building up charge, then you don't have a capacitor. So remember, our very first definition of a dielectric is it has to be an insulator. So pure water does not conduct electricity. It's only water with like salt ions and things in it that will conduct electricity. So what will happen if you put these water molecules in there? Let's just draw some, right? You've got them kind of all over, a bunch of bent molecules in here. What happens in the presence of an electric field to a dipole? It will line up. It will align itself to the dipole. So instead of all your water molecules being just randomly oriented, they're going to orient in this way. Why do they choose that way as opposed to the other way? Well, because by lining up this way, you get delta negative. This way you get delta positive, right? So those negative and positives are interacting with one another, right? That's an electrostatic interaction. So it will line them up so that positive and negatives interact with one another, right? Just like that. So essentially, by putting a material between this parallel plate, and you're putting a material in that can be polarized, you can stuff a whole lot more charge on these surfaces. So I want you to turn to your neighbor and tell them something that didn't make sense about dielectrics. And we're going to address it. Because if I ask the question, nobody says anything. So tell your neighbor what didn't make sense. Okay, what didn't make sense? Was there anything that was unclear? What did your neighbor say? It's not even what you think. You can blame your neighbor for not getting it. Josh, what's something that's muddy a little bit?
I don't understand why water can't conduct, like pure water can't conduct, but I
Good question. I'm just going to avoid going into a lengthy thing by saying that pure water looks like this. It has a band gap. Pure water doesn't have electrons that can travel from molecule to molecule without a big increase in energy. And there's estimates on what the band gap is. It's greater than like 5 or 6, though. It's a big band gap for pure water. No, you could get dielectric breakdown, which we'll talk about in a minute. But water that is now not pure, it conducts due to, if it's not electrical conductivity, but you have ions in it. Let's go back to our ceramics right here. Your total electrical conductivity is due to both ion and electronic motion. If you've got dissolved salt and chlorine, those things can move, because they're in the liquid state, they can move really easily. And so it's these ions that allows electrical transport in water. This is why salt water is so much worse. If you drop your phone in the ocean in salt water, it's really bad. If you drop it in your sink at home, like, it's not as bad for many reasons, but part of that is just it's much more conductive. Okay? Anything else that wasn't clear that I can explain about dielectrics on why on earth we get this extra surface charge in dielectric materials? This was just crystal clear, huh? Okay. So because putting a material inside of it allows you to increase the capacitance, we need two equations, right? So here's the equation for a vacuum. We're going to modify that if there's a material inside. It looks almost the same. In one case, it's epsilon naught. And in one case, it's epsilon. So what's the difference between epsilon and epsilon naught? It's simply this, that epsilon is equal to epsilon naught multiplied by a scaling factor, which we're going to call that's epsilon r there, right? This is just a number. It's unitless, right? So the units of epsilon is still the same units as permittivity of free space. It's still farads per meter. It's just that it can be larger than 8e to the negative 12. In fact, it can be really big, right? Some materials have really quite a large amount. So I listed that. So in the early days when they made capacitors, like think of like Faraday and like the old Tesla movies you saw where they had like these stacked up capacitors of like the early precursor to batteries. They'd build these galvanic cells, they'd charge them up, and then they would discharge it, and it would sort of jump the arc between them. In the early days when they did that, they didn't have very good dielectric materials. If you don't have a good dielectric material, you can't build up a lot of charge. And without a big charge, you can't have a big current, like if you wanted to make one of these big arcing things, right? So they were pretty bad, and they were gigantic. But a few years later, material scientists figured out how to have materials that generate huge surface charges, okay? So again, we've already talked about the reason why some materials are able to accumulate so much more is that they're polarizable. In the presence of electric field, this thing which was not aligned to it, when you apply electric field, it becomes aligned to it. And we showed that with water, basically the same thing happening there. So we've already talked about that. Something that this leads to, D is the surface charge density. So P is the polarization, which is just the charge divided by, charge over area, or the area, I should say, right? But D is your surface charge density. So you can figure out what is the surface charge density by just multiplying your dielectric constant times the electric field plus the polarization, where polarization for many materials is given by this. The total polarization for your compound is equal to the permittivity of free space, epsilon naught, ER, that's your dielectric constant, that's just an integer, right? Multiplied by the electric field. So that's the polarization you can get. So nowadays, we have capacitors which can store crazy amounts of charge in extremely small areas. We don't have to rely on big surface areas for our capacitors anymore. If you've ever taken apart an old electronic device like a radio from the 60s or something, you probably saw these giant black capacitors which are just enormous. And that was one of the things that made electronics not miniaturizable. So capacitor size versus time. Let's see what comes up. Let's see pictures of some old capacitors. Do we have anything? No? Really hopeful. Capacitor, old, large versus small, maybe? Yeah, so in the old days, if you've taken apart an old VCR or radio, some of these capacitors were just gigantic, right? So we figured out how to make them smaller, and it wasn't just by increasing surface area. These things are almost always round because they start out with a parallel plate capacitor, and then they roll it up. They roll it up, right? And so you can get quite a bit of surface area by doing that, but now we figure out how to make them better because we have new materials. So if we're going to make a new material that holds more charge, we need a bigger polarization. And in some molecules, like water, this is just a dipole. This isn't even a very strong pole that exists on this. It's slightly polar. So we got to do better than that, right? So where else can we look to for polarization in our molecules? Well, there's sort of three ways, 3 or 4. Let's go to them, right? So here they are. You can have, first off, the electric field. So if you have an atom, and it's got its nucleus and a bunch of electrons around it, if you apply an electric field to that, the electrons themselves will shift, right? If the field goes that way, the electrons will go that way, and the nucleus will go that way. Okay? So this technically has a polarization. It's not a very big one though, right? The electronic component, which is what we call this because it's due to the electron cloud, is typically a small contribution. So what else can we have? Well, let's look at ceramics. In a ceramic, this could be something like sodium chloride, where you've got an anion, which is larger, and a cation, which is smaller. The anion is going to be negatively charged, whereas this thing's going to be positively charged. If I apply an electric field to this, because I've got different charged ions, they can respond, right? If the electric field goes that way, these things are going to shift. This thing shifted that way, this one shifted that way, and so forth, right? And so you see that slight shift of literally the atoms moving a little bit from their default spot, that could generate a big polarization in ionic materials. Yeah, Josh?
Does that shifting go where, it's small, but does that actually change the shape of the...
Yeah. By the end of class today, if we have time, this is how piezoelectrics work. if you've ever heard of the word piezoelectrics or a piezo motor, like these linear scale motors that do very small, fine movements, they do that by applying a small enough voltage that your ions are literally, or your atoms and ions are shifting in the lattice. So very, very sensitive XY, motors are piezo motors, and they do it by applying a controllable voltage which causes atoms to shift. So we're going to come back to that. So you've got ion movement, you've got the electron cloud. We already talked about rotational or orientational, right? And this is like water molecule. Like literally the whole molecule could rotate in response to electric field. So these three things together are essentially how we know how to make better capacitors. Okay? So the total polarization actually is all of them together, right? You might have one that's dominating. In water, orientation's dominating, I'm sure. But in other materials, these can be larger components. And they have a different frequency response, right? So what do I mean by frequency response? If you're a positive or a negative ion, you respond to the electric field. Well, what if that electric field is switching directions, right? Right? So let's do a demo, right? When I raise my hand this way, like everyone raise this hand like that way. Everybody. Okay? Or no, even better. Okay, no, let's do this. All right, we'll do this. Okay, we'll do this. When I go that way, switch the other hand. That way. And like there's some like rate at which we can do this, and then we can't do it any faster. But it's pretty fast. Okay, now Elias is going to help us out here. So come on out. Now imagine this. Instead of just like flicking his hand, I'm going to do the same thing, but you this time are going to have to take like a giant step, like left and right. Okay? Like huge step. Okay. Just like go that way, this way. Right? Like see how like he can't respond nearly as fast? There's a different frequency response. Yeah, thank you so much for that. It's the same way with polarization. These three things that I showed you, they respond on different time scales. So let me ask you this. I think this might be our first clicker question. Let me double check that I'm not going to tell you it. Yeah, okay, right here. Our first clicker question is this. Which polarization would only be observed at a low AC frequency? So a low frequency means it's switching really slowly. I think that that's a wrong question. I think that's supposed to be a high frequency. Let's change it to be high, and I'll make sure that I grade the correct answer appropriately. So the question is, which one of these would you only see at a high frequency? High frequency means it's switching really fast. Of those three, electronic, ionic, orientation, which one only happens at high frequency? Okay, so, oh, sorry. Get your answers in now. Okay, get your answers in. Okay, we're going to close the poll. What do we think? If you're having issues with it, you can email me after class. We'll sort it out. I'm going to close the poll, though, because we're short on time. So, if it's really fast frequencies, what can respond? Yeah, electronic, definitely. And then really slow, you should get all of these things. Which one's going to fall off in the middle, ionic or orientation? So which one's the slowest? Orientation. The whole molecule moving, that's going to be slower than an individual ion shifting, right? So at really low frequencies, you should actually see all three of these. And at high frequencies, you should see them start to fall off. And so we see these curves that look like this. The polarizability typically looks something like this. Your maximum polarizability is highest at low frequencies. So if you're switching at a really low frequency, you get this big polarizability, right? And then, as you switch it faster and faster and faster, you are eventually going to drop off orientation. It just can't respond fast enough, and so it doesn't, right? And if you go faster still, it'll go to electronic. What do we care about this for? What would you use this for? Does it have any use? I mean, it's clearly like science, but like, can you make something out of it? This is just a yeah science moment. No, you can make things. Well, let me ask you this. When would you like to control, when would you like discrete events to happen as a function of frequency? Right? Something could happen with this that will happen as a function of frequency. Is that useful? Josh, what do you think?
Well, I was just saying, based on the frequency of the current, you would determine maybe what kind of materials
Is there an application for that? What do you think? Processors where? Where would they use this? Well, let me ask you this. Let's say you wanted to write memory like this. A polarization, if it stays there, right, if there's something called what's called a remnant polarization, meaning when you apply a field, take the field away, there's some leftover polarization, which we will get to in just a few minutes, I hope, right? If you want to write memory, and you want to write memory quickly, do you want to do so by reorienting molecules, or do you want to do it with electrons? Electrons would be best. The problem with electrons, even though they're the fastest, they don't stay put, right? They go back. But ions can stay put. And so ferroelectric devices operate in this regime, which is faster than orientation. And solid-state memory, there's a couple ways to make memory. One of them is literally due to that. You switch a polarization, and a little bit of it stays there. And the switching polarization is due to ions shifting positions a little bit. Which is why if you have solid-state memory and you heat it up, you delete it. Magnetic memory, it will also happen, but it's a different mechanism. Filters, though, frequency filters, like for speakers, if you want, a tweeter versus a subwoofer, you need to parse out the sound waves and maybe only keep the high end or only keep the low end. Dielectric materials work as band pass filters, right? You can only have parts of the frequency spectrum come through because it just can't respond fast enough. Okay? Yeah.
Why does the curve exist the way it does, or why does it pop up? It drops super low.
Yeah, it's called loss, dielectric loss, and it's tricky to explain. It has to do with the signal switching at a region which is almost fast enough for you to keep up with. Like so, Elias, come back up. Right. So, same thing. You're going to take a step that way, so go ahead. That way. No big deal. It's an elastic response, right? I apply a signal, we get some elastic response, right? And then this is like clearly too fast. But what about in the middle? What if it's like this? Like that we call loss. That is called dielectric loss. And in those regions between there, you suffer large losses because the ions or atoms or whatever it is that's being polarized can almost keep up, but it leads to large losses. So this is useful. This is how microwaves work. Large losses, that's where heat is generated. When there's large loss, like he's gonna get the most hot from like his body working out in that intermediate region. If it's nice and slow, no big deal. If it's too fast, he's not going to bother. But he's going to get warm from working out if I do that in that middle region. Microwaves are tuned to have a oscillation frequency of their electric field. By the way, this is how microwaves work. They heat up by oscillating electric field in there, right? Electromagnetic waves. And the frequency they choose is right at the loss function of water. This was the amazing thing about a microwave. In the early days, they sold it as this amazing device that it heats your food up. It doesn't heat your plate up. Technically everything's going to heat up as you're moving ions around a little bit. But they tune the frequency of your microwave to ideally just cause water molecule reorientation to happen, which should heat up the water in your food if you're eating food with water in it, which is almost everything, right? But not your plate. The problem is that like the food heats up and it transmits heat to the plate and it still feels hot. But it was designed to only heat your food up. And it uses that loss function. Yeah, Thomas?
So a dielectric can either be classified electronic, ionic, or orientational.
Or all three. All three might be present.
Even if the material can be electronic, even if it's not an ionic, if it's an ionic material.
So all materials have electrons. So electronic is always there. If the ions can move easily, then you'll have an ionic component. And if somehow this thing can rotate, then you'll have all three of those. You might not have that, though. It might be that they really can't rotate, and so you don't see that big rise at low regions. Sam? That's it? Okay, let's keep going. So obviously, if you want to get more charge, right, if we go back to our initial expression here, way back, a bigger capacitance, let's say you're trying to make the largest capacitance possible, you have options. You can make a larger surface area. You can make it thinner. You can put a material in there that has a large polarizability. But if you still want to go like higher and higher charge, what they'll do is they'll increase the voltage. If you increase the voltage across this, for a given thickness, the electric field will rise, right? If the electric field rises, then you get more and more capacitance. But there's a problem. If you go too high, you create lightning, right? Lightning is just dielectric breakdown of air, right? So this is not air, this is glass. But it looks the same because it's the same phenomenon. In both cases, in this one, this was like where they put one electrode, and the outside was probably coated with metal before, with like a metal tape all around the three other sides. And they just increased the voltage between the outside and the probe until you had such a large electric field that you started doing what Josh was alluding to earlier, that you have your filled valence band, empty conduction band. Under a large enough field, you'll actually strip electrons across that band gap, and you'll strip a lot of them. So now a whole bunch of electrons start moving very, very quickly, and that causes localized Joule heating, which melts your material. It completely destroys your material. So even materials like ceramics, which you're like, oh, this doesn't melt until 3,000 degrees Celsius. If you put a large enough electric field on a spot, this looks like it's melted because it did melt, right? So dielectric breakdown leads to pinhole failures where locally melted is really what's happening there. And so all materials have a fundamental limit, which we call the dielectric breakdown, right? Which is some electric field, and if you go above it, you will get lightning, right? You'll get current massively traveling in one local spot, which will melt your material. So you can't, the bummer here is you can't just increase voltage and keep on increasing it because you'll reach a limit where you have dielectric breakdown. And that also means you can't just go with the same voltage arbitrarily thin, because the thinner you make it with the same voltage, the electric field goes up, right? Because electric field is voltage divided by distance. So if you go too thin, the electric field could be large enough that you get breakdown, even with like a 9-volt battery. You're like, how did a 9-volt battery break this down? Well, that's how, because you made it too thin, okay? So what are these things typically at? The dielectric constant, this thing that increases the polarizability, epsilon, I guess we were calling it epsilon R, but here I've just written epsilon. In the early days, they didn't have very high dielectric polarizability, so the numbers were like 4, 3, or 10, right? They used like mica clay, which I think had like 80, and they were really excited about 100 years ago. Nowadays, we have materials that have a dielectric constant of like 10,000. So that is massive. These things are incredibly polarizable. So what's going on here? We're almost out of time. Gosh. So next class, we're going to end here, but let me say next class and Monday is going to be on sustainability. And the TAs actually requested to teach it, so I'm all for it. I'm excited to see what they have to say. They're passionate young people, and they're going to teach us about sustainability. But I am going to steal 10 minutes of Friday to finish ferroelectricity and piezoelectrics. And so watch for some specific readings for the sustainability. I think it's a really important topic, and they're going to come up with some really interesting things to read about that'll lead to good discussion. So watch for that announcement.